Okay, thank you very much. Good morning, because here I'm in Rio, so it's 6:30 in the morning, and a good afternoon for you. Thank you for the organizers for inviting me. So the title is indeed very long, and let me explain why. Because in these talks, I will do, in fact, two things. First, I will recall the results of two relatively recent paper, a paper from 2022, which is number one on this slide, and then for a PRL more recent, 2023, and they are both about the Galerkin truncated Burger's equation in 1D, okay? So these are the results I will first recall. Then, so these works, sorry, was done with people listed here. Okay, and basically the result of this work was to find a new temporal scaling that was unpredicted in the standard perturbative renormalization group, and find it numerically in the 21 paper, and in the 23 paper with Leonie Canet, find a justification from the non-perturbative functional renormalization group, okay? But both these works are in 1D. So this talk is also about the possible extension of these 1D results to 2D, title of the conference having 2D in it. So there is a problem for this extension, and it's a problem that not everybody realizes, and it's very simple. In fact, if you look at the Burger's equation, so the Inviscid Burger's equation is the one that is written here. You can very well see it takes two lines of algebra that this term, when you compute the derivative of the velocity square, this term integrates by part only in 1D. It gives 0 only in 1D, and in 2D, it doesn't leave 0. Thus, the so-called energy, which is the integral of the square of velocity, is not conserved in 2D, but it is conserved in 1D. And this is a problem. I'll come back to it later. So, okay, let me give outlook of my talk. I will first give the physical motivation, then the definition of the system, especially what we mean by spectral truncation and conserved quantities, and the stationary probability. Then I will briefly show the numerical results, well, that's the main results are about the scaling of correlation times. Then I will summarize the results from the functional renormalization group in 2D and in 1D, and then I will talk about possible extension to 2D system and give my conclusions. So the physical motivations. This 1D system is perhaps the simplest system in which one can study absolute equilibrium, okay? It is well known that the temporal fluctuations around equilibrium have a correlation time that scales like k-1, and this is very general, does not depend on the dimensionality of space. It's found in the Euler equation, in the Inviscid MHD equation, and also in the Gross-Pitayevsky dynamics. Note that when you are in t dimension instead of one dimension, the absolute equilibrium, that is the steady state spectrum, scales in space as k to the d-1. But this k-1 scaling is still the same in all dimensions for the correlation time. Just thus, it cannot be simply related to an eddy turnover time. Okay? Physical motivations, continuing. K-1 is the same scaling as the sweeping effect in turbulence, but sweeping effect is a sweeping by the large scales, and in the absolute equilibrium spectrum, you cannot say that the large scales dominate the spectrum because of the K to the d-1. Okay, if you add to the Inviscid truncated Burger's equation a dissipative term and a noise term, the system morphs into what is called the 1D KPZ equation that is well known by people in statistical physics studying interface growth. Well, in this system, the perturbative renormalization group that has been used since the 70s gives only K-2 temporal scaling for the trivial linear problem and K-3 for the 1D KPZ. So what goes on with the K-1? Okay, here I've given some reference. Those are the old papers, Forster, Anderson, Steven, and the Dominicis. This is the KPZ paper, and these are more recent papers about the KPZ problem. There are some mathematical motivations that I will just quickly mention here due to the Fields Medal of Martin Heyer that was on the correct mathematical treatment of the KPZ equation. So let's go to the system definition. So if you take the 1D Burger's equation, I said generalized because I add a lambda in front of the nonlinear term here, a nu for the dissipative term, and a square root of d for the noise term. The noise term is taken to have this correlation, okay? And note that there is a derivative in the noise term, and the so-called interface height is just the integral of the velocity field. And when you do this, this system is equivalent to the KPZ standard system, which is written here. In what follows, we'll study three different limits. Sorry, one is when lambda is 0. It's the trivial, so-called trivial Edward Wilkinson case, where you expect a K-2 scaling. If both nu and d are 0, then this is the Inviscid case, the Inviscid Burger's case. And when all the coefficients are 1, it's the KPZ standard case, sorry. Okay, I'm showing you here, just to give an idea of what we are talking about, some low resolution runs performed on a laptop. You can see here the velocity field as function of space and time. Here is a space and time, and here it's a movie. Space and time is time. So this is the linear case, this is the KPZ case, and this is the Inviscid case. You kind of see that there are differences by looking at the things by the eye, but it's better to look at correlation function to understand the difference. So let me briefly define spectral truncation. So if you consider 2 pi boundary conditions in X, so the velocity fields, you can fully expand it like that, then the Inviscid Burger's equation turns into this equation for the Fourier coefficients, and this conserves the total energy. It's very easy to check. By the way, integrating by part the nonlinear term, you see that in fact you have an infinite number of integrals, conserved quantities, and the energy corresponds to the case n equal 2. Now, defining the spectral truncation or Galerkin truncation, you introduce a projector that kills all Fourier modes larger than K max, okay? Because of this theta heaviside function is 0. If I project a field, I put to 0 all the Fourier modes that have a K in modulus higher than K max, which is, by the way, what you do every time you do a standard numerical integration, because you use a fast Fourier transform and there are no K greater than K max, where K max is half of the resolution. And so Galerkin truncation amounts to this replacement, project every term in the equation. When you do this by just applying the definitions, the Galerkin truncated version of the equation looks like this. So there is this theta that comes. And thus the nonlinear terms look like this with explicit heaviside terms like this. And okay, to cut a long story short, when you do this, you can find that on the infinite number of conserved quantities, only 3 survive the truncations. And these are three conserved quantities I've noted here, P, E, and H. They have a physical interpretation. P and E are respectively the momentum and the energy of the system. And the third surviving conserved quantity can be used to define the Hamiltonian. I will not go into that. It does play a role, but only in very special, for very special choices of the initial conditions. So I will not talk about that anymore. So what about the statistical distribution, the thermalized state, the absolute equilibrium? So if this equation, you can check it has the Liouville property, which is written here. Therefore, you have a microcanonical distribution that is conserved by the Liouville equation. When the number of degrees of freedom is large, you can approximate that by a canonical distribution. And here I've written the Liouville equation for the probability. And you can check, of course, that the canonical distribution is a fixed point of the Liouville evolution. And by the way, this canonical distribution, because the energy, remember, is quadratic, so it's just a Gaussian, and you can check that this absolute equilibrium is a white noise in space for you, and therefore for the interface height, which is the integral, special integral of U, it's a Brownian process in space. Okay, so the stationary solution is a white noise in space for V. Now, what about when we add noise and dissipation? So here, the interesting things comes because with the choice of noise we've taken, the derivative of a Dirac delta, it turns out that if you look, for instance, at the trivial lambda equals 0, so the Edward Wilkinson linear model, so just the equilibrium between the viscosity and the noise term. By the way, this, when you add noise and viscosity, the Liouville equation morphs into a Fokker-Planck equation, which is written here. And you can check that the distribution we found before works for this case because it these two terms cancel and this term is 0. So provided that we choose this relation between the temperature, viscosity and noise term, which is called the fluctuation dissipation relation, provided we choose this, the equilibrium is the same whatever the value of nu and d, provided that they check this. So the equilibrium will not change. So maybe I need to accelerate a little bit because I have only half an hour. So I will go very quickly about the numerical method. The numerical method is absolutely standard. There is only one trick, is that when you use de-aliasing, if you de-aliase the quadratic term, everything works fine by using the two-third rules. But then if you want to check the conservation of the third order term, you have to be careful and you have to compute it by v square, and then de-alias v square, and then multiply by v, and then de-alias, and then this thing is the good conserved quantity, and that's the only trick, okay? Numerical methods, they are standard, completely standard, except in the, well, it is also standard. In the case of large viscosity and noise, there are implicit methods that work for the noisy term. I will not go into the details. The way this is computed is we have a parallel code that goes into a large number of realizations, independent realization. We start them with the equilibrium distribution, and then we integrate in time and take averages both in time and number of realizations in order to have a mean of the correlation function. Okay. Now, okay, when you do a typical run, we will choose the periodicity length to be always 2 pi. When you do this, you have 3 basic parameters. One is the resolution you are using. One is the U root mean square. And then because the noise intensity is fixed, everything is fixed once you have fixed these two things. So sorry, these two things are the resolution, URMS. There are three things. In fact, I need to fix also nu to determine D. So at a given resolution, okay, and at a given URMS, in fact, I have only one free parameter, which is the amount of viscosity I put. So physically, this parameter you can understand as a Reynolds number. So remember, this is Berger's equation, so you do have a Reynolds number. The Reynolds number depends on the scale. I've given it here. And so you can define the truncation scale Reynolds number. And now, so because we fixed URMS to a fixed value, at a given resolution, the only free parameter we have is this truncation scales Reynolds number, okay? And that's the only thing we can vary. So on general grounds, what do you expect? Well, when this Reynolds number is very, very small, you expect to find Edward Wilkinson. When this Reynolds number goes to infinity, you expect to find the Inviscid scaling, and in between there should be KPZ. So how do these things go together? Well, first of all, let's check that then it works. So here I have a plot of the correlation. These are line levels of the log of the correlation functions as function of log of time and log of wave number. And you can see here on the left the Inviscid scaling, which is k minus 1. The KPZ scaling here, which is k 3 halves, and the Edward Wilkinson scaling, which is k minus 2. And here you have a plot of the crossover. So let us study this crossover better. To do that better, we will compensate it by the KPZ results. So KPZ here, so it's compensated. This is the correlation time multiplied by k to the 3 halves. So it is a flat for KPZ. For Inviscid, it's going up like that. And for the trivial Edward Wilkinson Lanotte thing, it's going down like that. So now the various runs have a various color according to the Reynolds number. The small Reynolds number are in red, you see. So when I get a very small Reynolds number, I can see that at large wave number, I get the k minus 2 scaling, okay? Intermediate Reynolds number, you can find them. So, of course, what happens at the truncating scales depends on the Reynolds number I've put, but the system goes to a renormalization group fixed point, which is the KPZ fixed point. So when I go to the infrared, boom, I get the KPZ scaling. And you can see that now if I increase, I need to increase a lot the Reynolds number, because if I increase it just a little bit at truncation, okay, it starts with the Inviscid scaling, but then it goes to the KPZ fixed point. But finally, when the amount of noise and dissipation is very, very small, you see this crossover, and the thing goes into the k minus 1 scaling here. This is the infinite Reynolds number, which goes all the way down with k minus 1, okay? So, by the way, this Inviscid scaling, k minus 1, you can sort of understand it analytically by you look at this equation from the equation of motion. If you take the second derivative of the correlation function, that amounts to take twice the first derivative. And when you use twice the first derivative, you can integrate by part, and you can compute numerically around 0, and you find this k minus 1 scaling. So if you now look at the scalings of the correlation function, so those are the correlation function rescaled with the correct thing. Here is the KPZ regime. Here it's the Inviscid regime. When you rescale them, you find this curve for the KPZ, and this is an inset of what is happening here. It goes slightly negative. And by the way, the solid line is some exact result by Stuhl. And here is the parabola you have in the Inviscid case and the numerically obtained case. So these are the two scalings. So now, in the I'm now turning to the renormalization group thing. So perturbative renormalization group that was started by Forster, Nelson, Stephen in their famous paper from the 70s, and that was later reused by KPZ. There are two known fixed points: the so-called infrared, the so-called trivial Edward Wilkinson and KPZ fixed points. So Leonie Canet in Grenoble, she suggested that maybe there was a third fixed point that could be found by the non-perturbative functional renormalization group, and that this third fixed point would correspond to the Inviscid scaling. So this is what she did. So I will go quickly into that because I need to finish and talk about the 2D extensions. So these are results. So you can see that here you have, this is a renormalization group flow, and you can see that it can go to the Edward Wilkinson, KPZ, or what she called Inviscid burgers, IB, case. So we do have three fixed points, and the third fixed point you cannot find in the perturbative renormalization group because it corresponds to an infinite value of the coupling constant, and the perturbation is in the coupling constant. So, but here we can find it. And now the beauty of the functional renormalization group is that you have an exact equation, and then you try to approximate the solution, and the more complicated approximation, the more exact result you find. So this flow diagram you have with the very simple ansatz, but if you complexify a little bit the ansatz, you get quantitative description of the fixed points. So, okay, now I have 5 minutes to explain the possible extension I'm suggesting to find things in 2D. So as I stated at the beginning of the talk, there is a problem in 2D, which is that the energy is not conserved. So this really puts a big strain on the method we followed, because if you remember, the method we followed works only because I can take the Inviscid limit, because in the Inviscid limit I have conserved energy, and therefore Liouville absolute equilibrium. It's this I lose. And by the way, if you look at the results for KPZ in 2D, they have two non-trivial, except of a simple one non-trivial critical exponents. So that's the problem. So what can we do? So I will not speculate on the possibilities of still studying the Inviscid limit on the Burger's equation, but I will rather suggest that there are known results. Here I've shown you two results by Spohn, okay, and another one by Leonie Canet also. So they've considered fluctuating hydrodynamics in the Gross-Pitayevsky equation, and in some regimes, so for those people who are doing fluid of light, the regime would be to have no vortices and only phase fluctuations, and then if possible thermal phase fluctuation, and then look at the dynamic of those phase fluctuations. So in this regime, you can find a KPZ universality class. So the idea I would suggest here, but leave for future work, is that, okay, there is, so I don't have time to go into the details, but if you look at this reference, everything is explained. Some finite temperature models of Gross-Pitayevsky dynamics. The idea is you can add, as you know, imaginary time, so-called imaginary time damping. So that means you add to the to the Gross-Pitayevsky equation a damping term that corresponds to imaginary time evolution, and you can add a noise, exactly like we did before for the KPZ problem. You can add a noise that compensates that in the associated Fokker-Planck equation, and this can be done following fluctuation dissipation so that you have exactly the same situation. That is, the absolute equilibrium will not depend on the amount of noise dissipation you put, and only the temporal scaling will change. So the 2D Gross-Pitayevsky system is a complex system, as you all know. There is a Kosterlitz-Sarless transition in it, with vortices appearing, etc. So the idea is to go below the Kosterlitz-Sarless transition when vortices are not dominant, and look at the phase fluctuation and see if we can find the KPZ. Well, we know the KPZ thing is there from the work by Spoon and the others. And the question is, can we find a transition when we go to zero viscosity, zero damping, and zero noise limit? Because we also know that the Gross-Pitayevsky system, when it's truncated and has no noise and no dissipation, the scaling is again k-1. So this is not something I'm going to do in the very near future, but I think it's an interesting problem that is left for future work. And with this, I just summarize very quickly the main results we had. So the 1D system, we found a new temporal scaling that was not predicted by the standard KPZ agreement, but the non-perturbative functional renormalization group allowed us to describe this new scaling in terms of a fixed point that is not caught by the perturbative agreement. So as I just said, the corresponding 2D problem could be studied, but probably within the spectral truncated Gross-Pitayevsky equation, because the Inviscid limit is problematic because of energy non-conservation in 2D in the original KPZ problem. And with that, I thank you and end my talk.
Thank you. So we have time for 1 or 2 questions.
Hi, Mark. I have one question. So did you check the height distributions in the Inviscid Burgers limit?
Did I check what? Sorry, I didn't hear you correctly.
The height distributions.
Oh, yes, the height distribution. Yes, we checked them, so I didn't have time to mention them. So in the KPZ limit, in the KPZ regime, it was the standard thing everybody expects, and we couldn't find very simple scaling in the Inviscid case, so it's still an open problem, but we did check it, yes. And the model, as described, works like everybody else model, I mean, like the one that are discretized in space that they usually do for the KPZ thing. You reproduce all the known distributions.
Okay, so do you expect that the height distributions will depend on the initial condition?
I don't know. This is a question you should ask to Leonie Canet, because she has some speculation in the Inviscid limit. There is some regime when you can develop exact results. So, but I would say I'd suspect that for very large wave number there is maybe universal distribution, but I'm not sure about it. The problem with the numerical results, I didn't mention that, is that when you take the Inviscid limit, they converge very slowly for large K. So you get it's very difficult to have an idea of what's going on really in the we need to do much more higher resolution runs. The largest resolution I used was 1024, and I think one has to go well beyond that to answer the kind of questions you're asking.
Okay, thank you.
Quick question. In 2D burgers, you said that energy is not conserved. Is that right?
Yes. Energy in the sense of the integral of V square, because the real physical energy is in the fluid mechanical sense is integral of rho V square, all right? And
yes. V
this
squared.
one, rho v squared, integral of rho v squared will be conserved, like in a compressible fluid, you see. But v square alone, its integral is not conserved, just because you cannot integrate by part.
Good, I agree. What's the decay law for that? Is that known?
No.
This-
I had a program. I don't think. Look, if you have no truncation, I don't. And if everything is converging, it should not blow up. The problem is you have nothing that guarantees that it will not blow up. So I don't know what happens. You cannot define the Inviscid system. So the decay law in Berger's case, I have no idea. It's a good question. Should ask Uriel maybe. Maybe he knows.
Okay, thanks, Mark.
Thank you. I think we have to move to the next speaker. So we thank the Marc again.